Did my question about unit conversion occur to you?
Yeah, absolutely.
Okay. Okay.
At first I thought, how could it be so miraculous? And then it wasn't until I realized that the whole thing was connecting as one single geometry, right? And then all of a sudden I realized, oh, no wait, this explains the miracle. The miracle that we have 5 dimensions, the miracle that they have boundary conditions called the Planck constants that tells us what they are. Like it both at the same time explained those things, right? That's
so
awesome.
So the what was it called?
Coherent system of units?
Yeah.
Yeah, that's what I should say.
The coherent system of units basically explains that magic trick. It looks like.
Okay. Well, it means you're missing or importing a misconception here.
Okay.
And that website helps us kind of walk us through what I mean by that. First of all, system of units, hopefully because of the S, makes it clear that this is a thing that applies to anything that has more than one dimension, because it's an S. And it's also a system that tries to reinforce that, right? So it's not just in a unit, it's a system of units. And it turns out that if you're in a system of units, it depends on how many dimensions are in your system that fixes the conditions of your system. So there's different coherent system of units, but there's only one coherent system of units if you allow all 5 dimensions. So the more dimensions allowed, the more restriction there is in how you should be arranging your dimensions if you want to be really making sense of these things. If you only have one dimension, if you only need a measure of charge, and charge is the only dimension you care about, then it's just the magnitude of charge that matters. And now it doesn't matter what your base of charge is, because all your comparisons of magnitude will be the same, right? But if you have charge and mass in your story, and you care about how these things interrelate, well, the rules for how they interrelate now fix things. So it now does matter what scale you're referencing charge versus mass.
Okay.
Right?
That makes sense.
And it gets more and more fixed as you add all 5 dimensions. So that's the short story. But the thing that might be unclear is that what we figured out in science is that there is a system of units that's best. It's best because it's coherent in all 5 dimensions, and that's the one we call SI, right? Okay, so we came to SI and adjusted our definition as we came to understand what coherent meant. Came to understand that there are rules in physics, so if you scroll down on that page, they'll tell us some of them. There's right there. So read this paragraph to me.
Okay. Each variant of the metric system has a degree of coherence, the various derived units being directly related to the base units without the need of intermediate conversion factors. Additional criterion is that, for example, in a coherent system, the units of force, energy, and power be chosen so that the equations force equals mass times acceleration, energy equals force times distance, power equals energy divided by time, hold without the introduction of constant factors. Once a set of coherent units have been defined, other relationships in physics that use those units will automatically be true. Einstein's mass-energy equation equals mc squared does not require extraneous constants when expressed in coherent units.
Yeah. Starting to fall in?
Yes.
So the fact that this is also part of the rule, in order to be a coherent system of units, you must fit your units together under these fixed prescriptions. So that's literally why it's all, yes, there is one unit that's best. If you didn't have these fixed rules to superimpose, right, then yeah, you couldn't pick one. But since we have not arbitrary rules that are fundamental to how nature works that we're using, then there is a system of units that's coherent. And there's only one if you want a full system that has all 5 dimensions. So in that paragraph, they mentioned that there's 3 of them. Yeah. But it just depends on if you do the 3-dimensional one or 5-dimensional one versus.
Right.
All right.
Awesome.
Are you completely clear on that or not?
Yeah, absolutely.
Oh, okay.
I think this clears everything for me.
Okay.
So in order to summarize, where I was confused was there would have to be, if it was not coherent, there would have to be some
There would be a constant of some number that's not 1, right
the
there.
non-1
Yeah.
right there.
And probably there too, and there too.
These
Yeah.
constants are all implicit in these equations,
Mhm.
but that constant of 1, since it's not explicitly shown as a 1.
It's not easy to notice that that was a point. Yes.
Yes.
It's a very central point of what we're trying to talk about here. Very easy to see because we didn't write the 1 down. You're right.
Right.
Good point.
Yeah.
Yeah. Okay. Good.
So, I mean, I think the thing that would make it more clear, if you
To
were
write it with the 1s in front?
well, no, I would just say perhaps something like, some kind of a ratio that kind of goes here. Write it down with that ratio and then say R equals 1 for coherent.
Well, yeah, we
system
could
of
just
units.
write it. We could just write it like this: force over mass times acceleration equals 1. To really make it obvious, right? We could just rewrite them all for
Yeah.
the 1 coefficient.
Yeah. And
Yeah.
that would have made and do a good job of explaining what coherent system of units actually
Good.
entails. That would be, I think
Okay.
that would clarify things
Yeah.
for
And
most
it's
people.
it makes sense that that's not an obvious thing to anyone at 1st,
Mhm.
right?
Right.
Because literally all the discoveries in physics were not obvious before. They were discoveries in profound, like E equals
Right.
mc squared. With any connection between these expressions in reality that's fixed, like when you find this connection like that,
Mhm.
it's a mind blower at first because you didn't expect it. Because you didn't know there was a coherent system of units. You
Mhm.
thought it was all random, and that's what made most sense, right?
Right.
Of course, this random assumption of what makes most sense made no sense of the conditions to begin with.
So it was the other way around from what my initial intuition would have been.
Mm.
My initial intuition would have been it is a ratio,
Mhm.
and you had to make it a conversion to get it to SI units.
Mm. I see.
So
I see.
the
I see, yeah.
so what
you were
this
like,
is-
no, this is a complaint, and you end up finding, no, this is exactly addressing your complaint, and that's why we invented these.
So there would have to be a conversion to get it back to
Otherwise.
a non-coherent
Exactly.
system of units.
Exactly.
Okay.
Yeah.
Yeah.
Great.
So
Okay. Good. That's like a central mystery of how you should connect or keep going with the rest of the story. So
Yeah.
great.
Yeah.
All right. Now, what do we want to do?
I'd like to start with geometry, actually. You have identified 5 balances in the hyperbolic figure 8 knot. And you have identified the partitions and the internal actions of each of these 5 balances.
Mhm.
It can seem like, and I shouldn't say that it seems like this for me, but the thought crosses my mind. This is a math trick. How do I know that this isn't a math trick? Where do you justify the geometries that
Well,
that you're using, or did you just play with the numbers until you came up with an answer that was
Look at this. Let's see. If we say x, so we got a general value there, -2, so we're fixing that. And let's cube it. That one. That one. This is a really interesting pattern.
So there's okay. So you factor.
This one's just
Oh.
obviously just x minus 1, right?
Yeah.
This one squared, we get an x squared. What is it? So x squared minus 2x
Oh,
minus
yeah.
another 2x, so minus 4x, and
So you're saying go
Plus
back,
4.
go back to the polynomial. Okay.
the next one would be,
So it's basically x minus 2 times that, right?
yeah, x times that
X cubed.
is x cubed minus 4x squared plus 4x, and minus 2 times that, so minus 2x squared minus 8, or plus 8x minus 8, right?
Yeah, okay.
And then collapse this to minus 6x squared. X is 12 minus 8. right, now let's think about a cube. Why? Well, because we're cubing something, but I mean, let's geometrically think about a cube. Let's just draw one and make it easier to specify all the things we're going to say about it, right?
Okay.
How many features of what kind, of different kinds, does this cube have?
It's got sides, vertices,
Okay.
and planes or surfaces. Or
Yeah.
surface.
Let's put area.
Area.
Whatever.
Yeah, it's got edges.
Edges. Edges,
That's what I
vertices, and sides. Yeah. Okay. So how many vertices?
meant. 8.
8. How many edges? 12. How many sides?
6.
6. How many volumes?
1.
Yeah, volume equals 1. Yeah, maybe I'll make that a capital V or something like that. All right, that's interesting. The coefficients of the cubic gave us all the features of a cube. Maybe it's a coincidence. My point's going to end up kind of being, though, this is the way all big discoveries have been found, by trying to find patterns, not knowing why they were there, and then looking closer until, aha! So let's do this one, or a square. So the a two-dimensional version of the thing now, right? So we just change our dimension from 3-dimensional cube to a 2-dimensional cube, which is a square. And now its features are
Oh,
vertices,
vertices
4,
4.
edges
4.
4, sides, sorry, edges, what were this? This is
Surface.
surface.
1.
1. Right? It works actually as it goes up all the way. It defines a connective structure now that we connect geometrically to the cube. Right? This has led to all kinds of powerful insights. Anyway, I think I kind of made my point. As you go up the sequence here, it continues defining the n cube of any dimension, right? And all of its features. Why? Why? What's the main thing we're talking about? We're just talking about a thing, a general thing that's being factored. There's one thing happening to it first, it's being subtracted by 2. But that's a constant in all.
So it wasn't.
Sorry.
It wasn't.
Sorry.
It really wasn't being.
That should have been a 2.
Yeah. There really was. I mean, you used the wrong word, which confused me a little bit. You said factored, but it was actually being expanded into a polynomial
Yeah, with these factors.
with these coefficients for each factor. Right.
Yes.
Okay. Good.
Yeah. Good.
Okay.
Okay, but now continue with what you were saying. We have these things and we want to know, well, how do I know that I can trust them in any way? Well, let's start looking into them. First one,
Okay. You're right.
pi, hyperbolic sine of 1/2 squared, squared, times my external rotation, 0, equals our fundamental derangements.
Okay.
This is our first equation for the time boundary, but you can also think of it as just our first equation for this. And this is the other half of it. It's this or this. Those are the two, both truths. What is this? The derangements of, since our n is equal to 5, it's just literally the rules for how 5 things can derange. Okay, it's making a claim there's a geometry set to the number 5. It's a unique thing. If you have 5, then there's only one way to base derange it. Now, let's expand this just to see if it pops out to your eye. There's a couple more things I can change. I can rewrite this equation because we know a whole bunch of things about trigonometric identities and gamma function and so on, right? So I find it useful to write it in this form. I'm going to change the pi to hyperbolic cosine of 1/2 squared times the absolute value of gamma of 1/2 plus I over 4 pi. I know it looks more complicated, but that's on purpose. Hyperbolic sine, this is still...
Is this absolute value here?
Yes. Squared. And then that. So this is the same equation. Interesting. What do you notice?
Well, first thing that pops out is the combination of the cos and sine hyperbolic.
Cool. And that their arguments are the same,
Yeah.
so that connects them, right? Intrinsically.
Uh-huh.
Great. But this one's squared, and this one's not. Okay, so one hyperbolic cosine, two hyperbolic sines, under the same argument though. Okay, good, those beautifully connect, it's easy. You can even just move that over there and make it look closer if you want it.
Mhm.
But this one,
It has a sphere of some.
yeah,
Well,
and that's an eye. Right, this is the imaginary part.
so it would invert a sphere somehow, or I'm not sure.
Okay, you're going. And what does the gamma function mean to begin with?
It's
What is this?
related to the factorial, 1 minus factorial minus 1, whatever.
Okay, so in terms of the functions themselves, the elementary functions, to be defining something that seems already like it is related to the definition of what derangements are supposed to be, right? We already know gamma functions are related to derangements, and we know that the gamma functions are hyperbolically generalizes, so we know it's hyperbolically expressed. So interesting. This derangement definition is telling us that we're having a trivial hyperbolic division happening. Balance too, we can use both words, I guess, right? But what kind of split? The hyperbolic split, which is doing what? Well, it's leaving something divided in half, but it's also in the imaginary direction, doing something with an inversion of a sphere. Let's look at this. If I draw the graph, this is just a regular xy plane. If I draw the graph of e to the x, less than 0.1, so it's something like down here,
Yeah.
goes to that point,
Yeah.
right? And that's e to the positive x.
Mhm.
But I can also do it the inverse
Right.
way, mirror image like that, and this is e to the negative
Right.
x. All right, so we have a basic splitting, and the hyperbolic cosine is defined as the average of these splits. So e to the x, e to the minus x.
Yeah.
So it's cosine of x is equal to 1/2 plus e to the negative x.
Oh, yeah. Yeah.
Yeah, and the hyperbolic sine is very similar in structure, of course. Just minus, yeah.
Mhm.
Equals 1/2 e to the x minus e to the negative x. Yeah, good. Well, that makes it something interesting. This one sine flip makes something very interesting happen in the structure hyperbolically. It means that the hyperbolic sine squared, well, first let's do the hyperbolic cosine. We can draw that in here. It's the average of these two. Great, we're going to easily can like that and like that, right? Cos of x. Okay, but what about the hyperbolic sine squared? Something like that. Okay, it hits down at 0. So there's a basic arrangement here between sinh squared and hyperbolic cosine. The first thing we might notice is that they intersect with the same y value in each case.
Mhm.
And we can draw a line through that and ask what's the y coordinate of that? And it happens to be equal to the golden ratio.
Okay.
What do we know about the golden ratio?
It shows up everywhere.
Shows up everywhere, kind of mysteriously. It's got a kind of cult following in a way, because everyone knows there's something going on with it.
Right.
But also, it's really intrinsically related to prime numbers.
Mm-hmm. Yeah.
Right? We have equations that have connected it to prime numbers. It's always associated with the number 5.
Oh, okay.
Right? So we're defining a system that's just the trivial hyperbolic system of division. That's where
Okay.
we're going.
Yeah.
What do I mean? I mean, we're sticking to the functions themselves as the things we're employing
Mhm.
for our structure. right? So this is a two-dimensional graph of how hyperbolic things divide things up, kind of giving you some kind of idea that there's this balance point and another balance point, right? There's splitting 1 and 0 is important. A lot of interesting features that then directly connect to the gamma function. Lots to explore just from that one picture. But the main point is we're only sticking to the trivial definition of hyperbolic division. We have a place under hyperbolic division. Okay, then what would it look like? This.
Right, okay.
Great. Well then, what would it look like from the outside? Well, it would have a rotation that, right? Because this thing is balanced as a derangement expression, not just a derangement, the trivial hyperbolic derangement. Okay?
Okay.
Good.
Yeah, no.
It's beautiful, actually, right?
Yeah.
It's talking about the trivial hyperbolic division domain, the domain under the trivial hyperbolic division. That has one characteristic way that derangements can be set that way. Yeah.
Okay.
All right. Next.
I guess I'd like to back up because this
Okay, good.
this is I think jumping into the story too far for me.
Where do you want
And
to
I'm
start?
not sure where, but I'm feeling like the piece that I'm still not grasping is the hyperbolic figure 8 knot. That so this is already after you've looked at the hyperbolic figure 8 knot and said to yourself, there's internal balances and external balances on this manifold, and it's the most fundamental manifold
The most trivial one. Yeah.
the most trivial that you can have. And then you said to yourself, I'm imagining here, and what are so you found this most trivial manifold.
First, let me dispel that's not how it works. I didn't generate an idea from a powerful insight because I got a lightning bolt from God's or something, right? That's not how it happened. It happened like this. I'm like, I don't know how to make sense of this mystery.
So this is where I want to follow this path, whatever this path happens to be. So and come up with and explain to you. So tell me how it happened. Tell the story.
So first of all, I have to contextualize it so it makes sense. I'm reaching for a story all the time,
Right, of course.
We don't have one. Just try to keep the way you keep honest is, well, we don't have a story until we can satisfy what conditions. We've clearly defined that in physics. We know what parameters we're trying to make sense of, and we just haven't. We also know how well we've measured them. So if you do provide me a story that did make sense of them, I know exactly whether or not I can tell you you're right or wrong, because I know how many digits you need to satisfy. I know how many digits I can call you on. Right? So it's very, very clear and established. But we don't have a story, so we need to be reaching for a story, always trying. I didn't want to start at the bottom and reach up with a story, make sense of one, and then find a way to see if it connected, because I'm not that good at math. Even if I had a story, I'd be sitting, okay, well, how do I see if that connects?
Okay.
I'm like, okay, well, I'm not going to do that. I'm only going to use the numbers. I'm going to use the data points themselves to look for a pattern.
Right.
And I asked every question I could for a decade from Wolfram Alpha. What do I mean by every question? You take the data points that matter literally are, there's 44 constants of nature. Right? And all those 44 constants in nature, when you stare at them for long enough, in my case it took years. So it wouldn't take, if you're really smart, you can stare at them for not so long. And if you notice in all of them, first of all, there's only 5 up to, there's one of them, a couple of them that are dimensionless. There's only 5 dimensions, right?
Okay, so the 44 constants of nature, that's kind of a curious number. And
Good go.
it's related in derangements kind of a thing.
Yes. This system, this base hyperbolic division, is doing what? Exactly 44 things. That's what this means. But they're not just arbitrarily 44. This number is vague to your mind. It just represents an amount. We're representing a very specific arbitration with this, right? But 44 things, those things.
Right. Okay.
So literally we're saying that this, even though it looks complicated, but you can collapse it to this, right?
Mhm.
I don't know, but this one might be mentally easier to keep track of all that's going on.
Well, this
I don't
one's
know.
kind of more intuitively because the hyperbolic circle thing.
Yes.
going here.
But it might lead you to not include in your mind the fact that one, this argument is 1/2 squared. That's got fourfold symmetry, meaning it could be -1/2 also,
Mm-hmm.
and it would still give you the same answer,
Mm-hmm.
right? Or it could have been -I/2, right?
Mhm.
Or negative. We got 4 of them that we can
Yeah.
basically make.
Right.
And then, since it's fourfold symmetry, means all 4 are actually happening. This one's showing you all of the actual 4. I mean,
Okay.
I guess once you know it, it's easier to calculate with this one, of course, or to write that one down.
Okay.
All right, but yes, good, great connection. The 44 things we want to explain are going to end up being the constants of nature, but that's not how we got to it. We didn't
Okay.
know that yet. We
Right.
just know that there's these constants of nature. This whole construction, we notice, is made of 5 dimensions. And eventually figure out that those 5 dimensions imply very important Planck constants, the Planck time, the Planck length, and this isn't just me saying this, right?
Mm-hmm.
This is all physics will agree with this, the Planck charge, the Planck mass, and the Planck temperature. Now, what are those? Absolute mysteries. What do you mean? Well, the absolute mysteries that come from this. Everyone that's got around and looked at these things has figured out, oh, these things imply some special boundary conditions called these. What? Yeah, the Planck time has a minimum boundary condition that's not 0. Right? The Planck length has a minimum that's not 0. You can't have 0 amount of space. You can't. You have to have at minimum the Planck length amount, and that's not 0, okay? And these have maximums. These are things we know about these, but they're implied from the fact that these constants in nature exist. Now, a little sidebar. What are the constants in nature? The constants in nature are the thing that makes sense of the coherent system of units.
Okay.
Right?
Okay, yeah.
Because that constant in nature implying there's 5 fundamental dimensions connected in some mysterious way we can't yet visualize. That's how we've been, right?
Mhm.
But it's very clear in the numbers. There's 5 dimensions connected in a very specific way, prescribed this way. That's physics, right?
Yeah.
So now we have this bit of information that's more important somehow, more fundamental or elementary. These things, it feels like, should be leading to these because we can kind of, only up to so many significant digits, get from these to these over and over. But they don't agree. When we try to do that from different constants and again, they disagree after 7 significant digits every time. Okay? That took years for me to notice. Because it didn't necessarily keep track when it was wrong. Right?
Right,
Yeah,
right,
okay.
right, right.
These 44 constants of nature only imply these boundaries accurately to 7 significant digits, and then they disagree. That's really interesting, okay? Now, I wanted to ask, where are these, if I'm thinking of these literally as boundary conditions, and we have 2 minimums and 3 maximums, then the simplest story I can imagine is that these 2 minimum conditions are balanced against the 3 maximums, and they close against each other, right? It seems like a thing, but
So did you
I don't
go
know what
to-
the boundaries
did-
look like.
Did you go to that conclusion right at this
No.
point in your thought
No, I
process?
mean, of course, this took me years, all of this, so it's going
Okay.
to seem way faster than anything.
No.
What I did
just
was,
want
what I did at
want
first
all the
was,
steps
is I
of the-
took,
of this- of the
as I took the
reasoning.
values we had for these,
Yeah.
right, we can write them down with our error bars, but you notice, except for this one, which has got a definition, we only know them to 5 or 6 significant digits, okay? I took all those values and I divided them by each other, multiplied by each other, took their different powers, added together. I took every simple geometric connection that I could connect or understand in a geometric way or use as an analogy to another geometric thing, right? That I could think of for, I don't know, I guarantee at least 100,000 questions for a decade.
All right.
And a lot of times 12 hours a day for a decade. You know, just over and over and over, write down a new question, like a list of questions, and then spend all day checking. And they take some time to check. Yeah. So I did that, and it eventually occurred to me to check, to parse these things. That was the big step actually for me, a big transition, not the, but a big transition. Each one, let's get one of them for reference. Which one do you want to pick?
Well, let's go with time,
Okay.
since that's the one we've got on board here.
All right, so the Planck time, where did I put its value? Right here. The measured value for the Planck time, not our predicted one, okay, is,
And this is the first one that you did
1,
anyway,
2,
right?
4, 7. I don't know, first I did these 1,000 times.
Oh, okay. Yeah.
Each. Yeah, so I had no idea what was first. 60. And first wouldn't have mattered because it was only when I had a list of them that all did something similar to each other that I realized there was a pattern.
Mm-hmm.
But let me get there slower. Times 10 to the negative 44 seconds. All right. So before, this is all we really knew about this mysterious boundary of time.
And there's there's a connection.
So if you
there.
want to say, I don't know what this number means, now we're starting from honesty. Perfect. None of us do, right? Nobody in the world knew what this number means. So let's just try to see if there's any way we can parse it to get more information from it. It's easier to use if there's a mystery in front of you, start with a piece of it and figure it out. How do we piece this now? Well, the only way we can do it is break into its number, which we don't know very accurately. Well, we know up to this many digits, but plus or minus 60 and the 47, okay? And separately, its power. But then you're like, oh, wait, but that's in base 10. Why the hell would anyone care about its power in base 10? Don't worry yet, we're just separating it for now. Okay, we pulled it apart into this numeric expression. Whatever that numeric expression is actually telling us, we don't know yet, but let's just assume it's a component of whatever this whole thing is, and this is a separate component of the whole thing. That's all we've done. Well, once I did that, I thought, well, if they're boundaries, then those two separate aspects should probably relate to each other somehow, if I need the system to eventually be symmetric, right? So I tried everything I possibly could, but of course, eventually you could just try setting them equal to each other and asking
Solving for
times
x.
by x. Or, solving, set it up so you can solve for it to separate. I did it lots and lots of ways, but eventually I asked, well, what if I piecemealed it so that they were all external rotations of some sort, and that was my x? And didn't know anything about this, but just knew this and that, and it spit out this, right? I'm like, ooh, that's gorgeous. Don't know what it means right away, first time I saw it, right? But I wrote it down because it was built only from fundamental things that we can make sense of. So right away, I actually saw it in this form, like, this is fantastic. But I didn't stop because I was asking 100 more questions of the day. At the end of that day, I also had a few other boundaries.
This piece here is like, wow.
Yeah. I was just in the practice of recording, and I didn't spend too much time on it until I got a list of other ones that were all also simple hyperbolic representations. Then it finally occurred to me, oh, they're all under hyperbolic balance, so I just need to define the piece, the balance each, right? I didn't know what the picture was yet, but they're on hyperbolic balance. But because of that, I started looking for hyperbolic shapes. Yeah, and then found, oh, the hyperbolic figure 8 knot, and now I knew how to piece it together and make sense of it. Yeah.
And so when you found the hyperbolic figure 8 knot,
Should write this there.
the balances,
X times E. Yeah, should do it like that. And then solve, right?
yeah,
Yeah.
okay.
Yeah. But this was probably, I don't know, 50, 100 questions in before I asked that pattern. Yeah, I was just looking for simple connections between things.
Yeah, so you found something that had a hyperbolic balance, and then you tried it with all the other Planck constants, and then you said,
No, first I tried it with all the Planck constants, and then found, oh my God, when I did ask the same question of all of them, I got not the same answer from any of them, but I did get a beautiful answer from all of them. And that's, first of all, that's a miracle, but a beautiful answer that was fundamentally hyperbolic in each case, right? So that, that made a big deal.
made you search for the
That
geometry.
made me wonder, what's the geometry that's hyperbolic, completely only hyperbolic? What would its pieces be? What geometry, what's the put together geometry?
Right,
Yeah.
right. Okay. So then you found the trivial balance, or the hyperbolic figure 8 knot.
Yeah. I found that the trivial minimum shape defined by geometers already, right? It was this, well, let's back up. There's a minimum 3 manifold called the Gies-Skeen, defined by the Gies-Skeen constant, or identified by the Gies-Skeen constant, right? And then what do I mean by minimum 3 manifold? Well, let's back up, and if we were making shapes from waves, but you were like pushing a wave and it went out, after you let go, it takes on a certain deterministic form, right? If you didn't push it hard enough, it's not going to make it over a peak, for example, or whatever. If you need to push waves around together so that they'll make a circle once, then there's a certain amount of energy you'd have to swing things around or push things around just right. And I know I do a lot of wave hand waving here, I think you gotta follow me.
Right.
But the amount of energy it takes to get something to trace a circle, but now after that circle hits that last point, then they're not gonna keep making a circle, because you minimally made one circle. You have to make enough energy to wrap it around into 2 circles so that the boundary of the first circle is holding together the part that's trying to fall apart, right? It's the minimum amount of energy required so that this wrapping now stays. Okay. This one is the minimum closing circle, but in 3 dimensions, okay? And if you do a double cover of this, so internally it's wrapping on itself and closing. So you can also get a hyperbolic figure 8 knot, which is also a geometric number. These are both numbers, but they're related. This one is 1/2. Sorry, 2 of these equals the hyperbolic figure 8 knot volume complement. So this volume complement literally is 2.02. I don't remember. I didn't memorize, but it defines the minimum definable volume that can be compartmentalized. Why? Because exponential is the winning growth. So if you're doing it all from exponential splitting, if I want to word it that way, or if you're hyperbolically, meaning the best possible way to divide things, then that's the limit, right? That's the smallest thing that can be folded together on itself under the fastest possible expanding action, right? Great, so we have a shape now
And
that's...
so that this relationship is actually something that someone else has already calculated, and that
Yeah, I had nothing to do with that.
yeah. And so if I wanted to look more into this relationship, what would you recommend that I?
Wolfram Alpha and Wikipedia right away, right?
Okay. Yeah.
Type in the number for the hyperbolic figure 8 knot, or you just type in the words and type in the number.
Okay.
And then type in a few digits on Wolfram Alpha, and it'll lead you down a trail of looking at things. This is a minimum volume complement that's geometrically defined by the hyperbolic functions itself, right? I can give you another full definition equation, but let's don't yet. Just try to imagine that there's a small shape happening, but it's important to remember it's the smallest possible shape. Not the smallest possible that you can imagine it could be or in your mind. It's the smallest one that can be folded on itself. Right? So
just from a
so it's great, a volume complement, but that's down there. If something's folding in on itself down there, all the fluid's falling in, what's happening out here? The opposite. Okay? So that volume that we've partitioned, by the way, is balanced by the opposite world outside that's oppositely partitioning. That's fair to say, right?
Sure.
What is that volume? The N hypersphere of maximal volume. It's the greatest volume you can get from a sphere of any dimension.
Okay.
The sphere of greatest possible volume in any dimension, the one defined that way in geometry, happens to be the mirror image of the smallest possible volume partitioning in geometry. Beautiful. Beautiful.
Right.
The 2 most beautiful shapes define each other. Fantastic. And even better,
They balance each other.
They balance each other and define in that balance the minimum trivial universe, domain of physics in which things are persisting, and the 5 dimensions or 5 fundamental actions of this division continue forever. Right?
Okay. So you still haven't figured out, or you have at this point in the story, you're beginning to look at the hyperbolic figure eight knot as the internal actions.
Yeah, I'm starting to understand, that there's an internal, external, both in every balance, but also that this full balance is composed of things that stay together on themselves and things outside that stay together. There's an inside and outside, yes.
Right.
Yeah.
Okay. Yeah.
Yeah, there's two meanings to inside and outside now. There's an inside of each balance, and outside of each balance.
Mm-hmm.
And then there's the whole partitioning itself has a trapped fixed inside and a trapped fixed outside.
Right.
And both of those trapped fixed domains define the most beautiful two geometries there are, which happen to prescribe all of the boundary conditions of
So this is
point
where you
constants and so on.
discovered the figure eight knot.
Yeah.
Is at this point in the story.
Yeah, well, of course, after checking all the rest of these and trying to interpret what that meant and so on, but yes.
So how, now you've got this equation, and so geometrically relating that back to the figure eight knot that you just discovered here.
Okay. So first thing you would notice is that this balance now seems to perfectly define the same balance here. So the gamma function hyperbolically generalizes. So it's talking about a thing that's hyperbolically splitting to begin with. Okay. But this and this are the opposites of each other. They're literally the opposite of each other. This construction of splitting is externally the outside splitting into a sphere, but internally.
Okay.
Okay.
Yeah. So so what I'd when you're relating that insight back to the figure eight knot.
Well, that really helped to get a
When-
picture of it, right?
Okay.
Yeah, at that point I was able to get a picture because at first I was working in the dark off of just math. I didn't have a visual model. And then I found Henry Siegerman's, and thank you, Henry. He posted an STL free access version of this, and then I just had my friend turn it into art graphics so we can see it better and stare at it forever. But noticing the first thing that's going on is there's an internal doubling of something. Something happens twice in there, right? And this external piece, if you think of the circle that's going out this way, it wraps all the way around. So it's doubling in there too, but it's spread all the way around like that, right? What's the next thing you notice in here?
It's got it. Well, I suppose it's inside, outside. It's wrapped around itself.
Good. And its main feature is that it's closed. Of course, these strips we took out so you can see inside. Right? Its main feature is, though, if you were an ant, walked all the way around, you would never fall off the edge.
Right.
Fantastic. So it's a manifold. Maybe we should talk a little about manifolds because that was also new to me.
Okay.
So here's now how I see manifolds. They're a good way to introduce manifolds. If you have a geometry, we're going to start with a two-dimensional one. Geometric shape, let's call it a rectangle. This is not a manifold, but it is a geometric shape. Pretend it held it flat and it was just a rectangle, okay? It is a geometric shape, but I can transform this geometric shape into a manifold, which is a special kind of geometric shape. I do it by removing its boundaries, and we mean that literally, but you can't just delete. That's not what I mean by remove. I mean by you make it so that its boundaries don't have any gap after them. Those boundaries close against each other. So we glue those together. And then those two boundaries are gone now, okay? But we have circular boundaries that we didn't have before. Now I need to bend that together and close this boundary against that boundary, which would turn this into a torus. So a two-dimensional flat sheet, and you have to allow stretching, but it can be transformed into a closed boundary we call a manifold. But to do it, you have to get rid of all of its edges. All right, which means if this shape is a shape composed of wave actions, they're nothing we're not responsible for. They're self-responsible. Then we're looking for boundaries that are, well, what do I want to say here? Well, feedback what I just said, just so I know how much of that followed.
Oh yeah, so basically you could take a two-dimensional surface and eliminate the edges and make a manifold on it that has an interior and exterior by removing boundaries.
Good. And notice that the action of removing the boundaries or edges. The action of removing the edges requires doing something geometric. Right? If you put this in a certain geometric form or twist or rotate, there's some geometric thing that has to be done to turn usually a shape into a manifold. But we're interested in all the possible actual manifolds, because all of those shapes have some intrinsic value to wave dynamics, right? If it's a manifold, then it can be self-balanced in waves.
Yeah.
Yeah,
Okay.
good. All right, so the big trick is then, well, how do we go from a two-dimensional manifold, which is actually really easy once you see it, right, the first time. How do I have a three-dimensional shape and turn it into a manifold, or a four-dimensional, or a five-dimensional? What does that mean?
That's harder to imagine. That's getting to the that's getting back to the dimension.
Yeah.
How do you?
I'm pretty sure everyone's stuck at that.
Yeah.
We have no visualization for the rest, I think. But now we do. So this is going to be a mind trip, because you have to allow yourself to try to think something never thought before by me ever before on this either, right? But what we're saying is that we have a domain under rotation of 5 actions all the time. Always the 5. That's why the presence of 5 dimensions is there. If you're in a universe, you can measure time, space, charge, mass, temperature at any point. It means something to be able to do that. But you can't say that about anything else.
So are these dimensions like it's difficult to imagine 5
Rotations.
five spatial dimensions.
Okay.
However, it's not difficult for me to imagine 5 dimensions. So if I first, Euclidean 3-dimensional space. Einstein comes along.
That's time.
He includes time into there, and it's like, yeah, I think I can imagine a 4-dimensional thing now. Including temperature and charge to this. Okay, yeah, I think I can, and then mass.
You mean you can allow for that to be there, but are you visualizing them as features?
I not in a spatial sense.
Not in a spatial sense. Okay, let's go to a spatial picture. We have a completely clear spatial picture, and let me sidebar for a second. I could talk about the whole picture in terms of temperature. I have 5 kinds of expressions. 5 kinds of expressions of time, 5 expressions of space, 5 expressions of charge, 5 expressions of mass or temperature. If I fundamentally wanted to think in one versus the other, we're used to fundamentally thinking in terms of space and pretend it's the background that counts. This is saying that time is actually more fundamental than space, and space is derived from it. Fine, but if you want to just visualize and still call this the volume space, then what we're saying is that, let me call it the soup. The soup, when it turns into this minimal balance, when it divides this way, turns into the hyperbolic figure 8 knot externally inverse dividing as the n hypersphere of maximal volume. As soon as that happens, all 5 of these actions are always happening in that domain. So that domain is 5-dimensional as a projected system. Okay. So those 5 division actions that are balancing against themselves. The internal boundaries are getting a balance against themselves. Out here is not required, right? In fact, out here is not doing anything. Eventually you get out there, it does nothing, right? It's less and less, or more and more as you go in. But really it's against the own internal boundary conditions where all the magic is happening. Okay, but that means that if we're in a system that has 5 perpetual, always there rotations, base 5 is the minimum you're ever going to get for a coherent system. We can't really be talking 3-dimensionally and think we're making sense of the picture. We're missing 2 dimensions to begin with. The minimum coherent picture requires 5 dimensions. If you go less than that, you're already in a picture that's not like reality very clearly.
So it's interesting though, when I'm looking at this, this length is actually 3-dimensional from when our conception of space. So does that mean there's actually 7 dimensions? If you split
I
that
see
into
what
3.
you're asking. I see what you're asking. So what I'm saying is, instead of thinking of the void as X, Y, Z 3-dimensional and we put stuff in it, now I'm saying that the void was a random soup that's no longer random. It's a 5-dimensional system doing a very specific thing. So it's got 5 expressions to begin with.
Okay.
So yeah, it requires that you delete the X, Y, Z void you're used to putting all of reality in.
Right, exactly.
Yeah. Put all that completely out and say, no, this is the minimum possible void that's nothing or nothing interesting. It could be just an infinite
Okay.
soup of nothing interesting
Uh-huh.
to the minimum interesting thing that could happen in that void.
Mhm.
And if it did happen, it would then be perpetual and persist, right?
Yeah.
Would be this.
Mhm.
Yeah.
Yeah.
So, I lost track of where I was trying to go. What question was I trying to chase at this point, or did we already do it? What did you ask last?
I'm trying to, I guess where we're trying to get to is relating back to the discovery that of this effectively that maps to that,
Mm-hmm.
and then be able to relate this hyperbolic equation right here back to the figure eight knot.
Yeah, okay. When you look at the hyperbolic figure eight knot, is it split in anything?
Yeah, it's got an internal and an external.
Uh-huh. And also the inside is like vortex arranged.
Yeah.
If you look down the throat, it's like things, or say they're coming up, or you're looking down the side that's coming out at you. They're getting split this way, and they're getting split this way at the same time.
Mm-hmm. Yeah.
So there's a double splitting happening.
Yeah.
All right, that's a start.
Mhm.
I want to kind of leap because it took me a decade, and I think you want the process of it. So
Yeah.
where would you go next? Or how would you interpret what I just said?
So in order for that process to occur, there has to be a balance of actions to hold things together stably.
Mm-hmm.
And that balance would have to be, I mean, just from a first blush, it would seem like that there may, in order to hold that structure in its complexity, there may actually be more than one balance, but something has to be happening internally and externally.
Oh, yes.
And
Be more than two-dimensional circle.
I wouldn't jump to the fact that there's 5 balances in this necessarily. I mean, I would know that there's 5 constants of nature.
Oh, I started with the 5 because we have the 5 dimensions. And then eventually, after thousands of questions, found that if I ask this way for all of them, I get an equation that Wolfram Alpha spits out that's just trivially hyperbolic.
So now you've got these hyperbolic equations,
Mm-hmm.
and you've got the knowledge that you've got a manifold that is the minimum
Mm-hmm.
stable
Mm-hmm.
structure in nature that has an external and an internal. Now, how do you relate these equations back to the structure that you just found that is a hyperbolic figure eight knot?
Okay, let's do, if I draw the graph of a hyperbola, it looks like what, this and like that. What's the main features of this graph?
Well, they asymptotically approach their coordinates. There's a distance here,
Mm-hmm.
and it's symmetrical.
Good. And this coordinate is empty. This coordinate plane and this quadrant is empty too, right?
Yeah.
So if something's being hyperbolically divided, so it's like this now, but then also being rotated just right
Mm-hmm.
on top of itself, what picture would you see then?
But I kind of see a throat here. It goes out to, if you just took this and rotated it
Okay.
around that axis, it would be.
What if
it would have a
instead
throat,
you rotated about this axis?
which this
You
one would-
rotated that by 180 degrees on top of the other one.
Yeah, then that you would have this up there. It would basically
No,
be
folded.
Folded. Okay.
Yeah.
So
Okay.
you
Yeah. Let's say let's fold again. That's a better way to say it.
Folded
Uh-huh.
that way, then those two would overlay each other identically.
Yeah, and then they would be agreed down here, so on top of each other down here. But out here now, we would get the full opposite expression. We folded it, but the whole outside is now on one side.
Yeah.
Okay. Okay, we're just missing now twisting things. That was just hyperbolic, okay, and we've folded, and if we take for granted that there is a minimum possible volume partitioning and that it has a known shape, or we know something about it, okay? We believe that there is one there. What does it mean intrinsically that that's even occurring? What can we infer from that knowledge alone?
That perhaps that would be the, that could be the fundamental structure in nature. I guess that would be the...
Maybe, or it would be a good candidate you would want to use to build a model from, at least, right? Yes.
Yeah.
But what else? Like, if we're making a minimum volume partitioning, think of the most trivial way to do something: rotate, twist things together to collapse off a volume, right? And then find the smallest way to do that. There's intrinsically two ways to look at what you just did. You can look at it from the boundary that you've cut off in, or from the boundary you've cut off out. The next clue, and so here's another 1,000 questions later, because you get to go through a faster process than me.
Yeah. Well, I've got a guided tour, right?
Yeah. These 4 rotations, or 5 rotations, I put the time on at sub-zero, okay, are the trivial most important parts of our balance, of our universe, the things we really, really care about. So what would the sum of all of them then be? That has to be something important. Here's the way I ask questions from opener alpha. All I need to know is that that's going to be something important. I don't have to have even an intuition for what it's going to be. I just need to know that I should be asking that question. What is that thing? And I have a way to get an answer because I have numbers for all of those, and I carry out to 14 significant digits, and I have that for all. So we add them all up and we get the answer, put it in a Wolfram alpha, and it spits out an answer for us. And we know how to translate every answer we get now in the binomial factorization prescription, right? It's for any constant in nature, well, actually it's more general than that. So we're using it right here too. For the entire construction, we have a primary action on a set of primary boundaries, and then we have 1 plus or minus the terminal action on the terminal fixed, always the same for every one, boundaries, and this happens to be the Planck length times by the Planck mass over the Planck charge squared, which sets the arrangement of the exterior world, which you perfectly, but also 1 times 10 to the negative 7, numerically. Yeah. So that means that this piece doesn't come into play in the answer until the 7th significant digit-ish. This part, plus or minus 7th significant digit, right? Except for how much this goes off of it. So that means we can ask the answer and know that the first piece will be somewhere, well, we can ask it around 7 significant digits. What does it give us? Piecemeal that, and then ask the second piece. And what do we get? I get this. Did I call it this with you? Big twist? Oh, no, it wasn't you. Big twist squared, a sphere divided by the real part of the omega 1 constant cubed. Do you know this constant?
I've seen it used, yeah.
And the terminal part is the inversion of that twist squared. And here we have a very special number. N is our 5 dimensions. Okay? V, so H star here, equals the dimension of n hypersphere of maximal volume. Feel like that took forever to write. Okay, so read this to me. What do you see? We have a 2/3 squared, and we called this big twist before in our hyperbolic figure 8 knot division. Let me put the 2/3 part aside and do the rest of it first. Because I think I haven't had that conversation with you. I'll let we produce it. This is a 4 pi, which means?
It's spherical.
Spherical. What is omega 1? You remember it from what?
From
Oh, from my stuff.
Yeah.
Okay. Well, it's intrinsically one of the 2 periods for elliptic geometries and the gamma function.
Okay.
It's built into all of our fundamental functions. So it's one of the constants of math. Okay. One of the beautiful ones. But it also has one that has the omega 2 that comes with, and they both have real and imaginary parts. Okay. Well, here, what's this one though? We have a sphere divided by 3 of these fundamental periodic actions in geometry. And over here we have the dimension of the n hypersphere of maximum volume being divided by the dimensions that we have, 5. What could this mean? And this is the exterior, the terminal boundary. So on the terminal boundary, we have this happening.
Right.
Okay, and the,
So it's
the,
relating.
the exterior projection of this is this. So terminal boundary, exterior projection. It's kind of, it's nice that these are opposites. I guess you can see how those cancel. But why are they there to begin with?
Yeah,
Let's get to that part.
so so it's relating the 5 constants of nature
Mm-hmm.
to
To 2 different actions. It does 2 things. It projects a sphere under division of this action, 3-dimensional division of it,
Uh-huh.
triply, right?
Right, so that's
Ignore
the,
this piece
the
for now.
external is kind
Uh-huh.
of spherical.
Mm-hmm. And we're still ignoring this piece for now. And out here, or on this internal terminal boundary, that's
Boundary.
responsible for that, by the way. But
Yeah.
what does it look like down here? Down here, it looks like not the 5 actions. It's the 7 point something or whatever this number is of dimensions of action
Mhm.
being divided up by those.
Mm-hmm.
But very specifically, these 2 numbers both represent dimensions.
Mm-hmm. Mm-hmm.
Yeah,
So it's an average,
it's
sort of.
you're projecting this thing under the 5 actions you had.
Right.
Yeah, yeah. So literally, this is telling you have a sphere and you have a hypersphere of maximal volume involved, right? And then we just can talk about these pieces, not just, but in the equation for the volume of the hyperbolic figure 8 knot. One of the equations. In the imaginary direction, oops. I don't know why I did that. 1/3. And the dilogarithm of, sorry, did that again. 2/3. And like that. Okay. So this is one of the definitions that bring this to the volume of the hyperbolic figure 8 knot. First thing to notice, it's composed of 2 things, 2 dilogarithms. These are logarithmic connections, think of a 2-dimensional logarithmic connection. But if it was just -1 in here and -1 here, that would mean a dilogarithmic flip. -1 means you've gone 180 degrees, right? So, but it's not a dilogarithmic flip. It's only 1/3 of that. And this one's not a opposite dilogarithmic flip, it's 2/3 of it. So what are we doing? We're dividing up in the unit circle, 1/3 here and 2/3, or sorry, you can go positive or negative. Either way, we get to the same line with 2/3 and negative 1/3, right?
Okay.
Okay. So this thing is fundamentally partitioning into a 1/3 twist and a 2/3 twist. I'll call them little twist and big twist,
Mhm.
so we can go
Okay.
along. But that's here at the volume boundary, at the volume of the hyperbolic figure 8 knot itself. Okay. So that twisting, that division twisting, is just inherently built into how all the things are connecting. There's a twist factor, right, and lots of things squared of it, but right here, the twists themselves are canceling in intersection,
Mm-hmm.
okay? And here, we have a sphere under triple periodic division, and here we have a hypersphere under dimensional division, or the dimensions of the hypersphere under the dimensions of the action of our rotation. So our rotational actions are basically projecting the construction they can get of the maximal hypersphere,
Mhm.
right? And that's externally what it looks like. This is what internally looks like. Okay, how much of that tracked?
Yeah, I think basically the sum of all the rotations is the external projection
External projection,
and the
internal boundary,
Yeah.
fitting against that projection. Yeah, these two
Yeah.
fit together.
right.
Yeah, yeah. But they're all the system. They're both true. But if you weren't going to look at it zoomed in very much, you could ignore this and say it's just this. Yeah.
Sure.
Okay.
Interesting. I suppose all of the other things that you published in the 44 derangements, mass of the all
Okay,
the
good, yeah.
standard
So
particles,
let's
and,
do-
and how you got to that, and
all that kind of stuff.
Yeah, we'll do exterior divisions for the hyperbolic vortex equation, and how that gives us all the partitions of charge, and how that gives us all the partitions of mass, which is, I don't know, what I just said in a short amount of time is unbelievably phenomenal.
I know.
Okay, and then
awesome.
and then from there we basically finished. Oh, and all the constants of nature. I think you've already got all that down, right?
Yeah, pretty much.
Okay, so we'll do the charge assignments, the mass assignments, and then we'll go from there into the awesome things that this connects to fundamentally in terms of math functions, like the gamma function and the Riemann zeta function, and so on.
Yeah.
Yeah, okay, good. I told you this yesterday, right? About they sent me an equation, said, I'm sure you've seen this, but just in case,
Yeah.
I hadn't seen it.
Yeah.
And I noticed right away that the point of his blog was to note that it was a way to geometrically get close to the fine structure constant. And I think it got like 6 or 7 significant digits right, which is the closest I've ever seen. And I've been trying and working to find equations to do this for a long time, right? So he sent this to me casually. He had no idea how big of a favor it was. I thanked him since, but he didn't care. Well, I could rework the equation very quickly because I cared about je. Instead of in terms of the fine structure constant, I reworked it so it wasn't squared. And it turned into this. pi/2. Okay, now, I really should always start with it just being an x, so people don't get confused. And literally mean I'm putting in a variable here, but it's the same variable every time. All right, so at first I just got this and had no idea what it was. You could first glance at it and say, oh, it looks very close to something I know, very familiar from something I've seen before. But at first I was just sent this and said, hey, when you do this, the x that you calculate, turns out one of the x's that come out of this is 4, is very, very, very close to the fine structure constant. And I said, well, what if I put the actual fine structure constant in here and say minus y? Then what's the y? How far off would I have to modify this equation to get the right answer all the way? And of course, as you know, this ended up being equal to the Planck mass. Every digit I needed. Right? The right power, the right digits. It blew my mind right away. Wait. Okay, I need to look at the geometry of this equation. Now let me change my variable to this letter instead. So you know it's now set, because once we set this, there are 4 answers, and I'm going to list them like this. Now, to say 4, let me draw them on the plane. There's je1 real close to 0, okay? Je2 is also on the real axis. Wow, I'm really got bad handwriting right now. 1 and 2. Je3 is about up here. And 4 is the complex conjugate, the mirror image down here, down there. Okay, these are all in the complex plane, meaning they have a number value. I can assign, they spit out a number to a lot of digits, right, for each. But they're all solutions to the same setup, the same geometric arrangement. Let's stare for a second at that arrangement, just to get in our head the intuition of what its components really are. First thing to notice is that it has one of these and one of these, and those 2 things are inverse. Cool. So it's joining a 3-part system. On the left side, it's talking about a 3-part system, and 2 of those pieces are joining opposites. I don't know what the things are even, but I know they're opposites at this point, right? The next one's related to the other 2 in that it's one of its factors is made up of, right? That piece is still there, but it's modified to being cubed and divided by a circle. All right, one quick side note, hyperbolic geometry. You've seen this projection before. What is this projection representing? It's a cone.
It's the asymptote, so the hyperbola.
The asymptotes of the hyperbolic connection, the domain under hyperbolic revolution, right? So if we're in this 4-dimensional hyperbolic space-time, which we believe we are, under this construction, it's a construction that has, if you imagine a plane dividing through here, something and its opposite, both in the picture, and a volume connecting around. It's a bit hand wavy, but you can kind of see a connection here. Another thing On this thing, there's only two pieces. What do those two pieces mean? The one on the right is really easy. It's the point mass boundary, and even if you don't know what that means visually yet, you know it's an important boundary we're keeping track of, so that's great. But this one, I to the I, equals e to the negative pi over 2. So I to the I to the negative pi over 2, you could say is e to the negative pi over 2, right? To the negative pi over 2. Maybe now it's easy to see what it is. This is a rotation to a rotation. We got two actions of rotation. I'm going to call these internal twists. Two orthogonal internal twists to the mass boundary. So now we're saying that this equation is saying we have a constructive arrangement that ends at the mass boundary. Inside the mass boundary, there's two internal twists. And we could call it just that. So ignore this side. This side, it's a thing with two twists inside the mass boundary. That thing with two twists inside the mass boundary is equal to being a thing composed of two parts that are opposites of each other, one part that's cubed and divided by a circle. But then the next big clue is to remember that this equation is the equation for the hyperbola, right? It's very familiar that we're talking about a hyperbola. If I didn't have the 2 pi, it would literally be the hyperbola.
Right.
So this is the hyperbola that's modified by the division of one circle. So I'm going to call this the self-closed hyperbolic connection. This geometry here is talking about the self-closed hyperbolic connection. And you can say that that thing is made of 3 parts, 2 inverses in this volume thing. Or you could also say at the same time, inside the mass boundary, it's 2 twists. Now, when you set that geometric condition, you say both of those things are true and solve, we get these 4 answers. Awesome. Why did it sound or pop up as interesting? Well, first, because J1 squared equals the fine structure constant, the central number, dimensionless number we needed to explain in all of physics, the one that's most centrally constructively there, right? Second, we always expected that if we ever got an answer that geometrically told us what this number meant, that there would be something profound that just cascaded off that, right? Let's see. This number, J1, comes with 3 sisters, right? Or brothers, whatever you want to call them. But all of them are actually part of the solution, so they should be also interesting too. They should be playing a role just as central and important as the rest. So they should have something to do with this whole system closing against its circular actions and its spherical projection, right? They should be responsible for it because technically this is the whole outside connection we're talking about. Okay, great. Well, besides J1 squared equaling the fine structure constant, these solutions themselves have geometric relationships that are beautiful. Absolutely beautiful. First, simple one. You can see this one. If you add them all together, what would you get? Just imagine they're all vectors. If you add all these solutions in the picture, then you can kind of see they cancel, right?
Yeah, 0.
0, okay. At first, if you didn't have the picture, that might be, what? You can add all those numbers and get 0? They look like crazy numbers. Cool. Remember, these two have imaginary parts to them, which means I could also, instead of representing 0, 1, 2, 3, and 4, I could have 1, 2, and then I could use J_R and J theta to represent them. 2 alternate ways to represent these 2. This doesn't mean we have more of them, just different ways to represent them. Okay, now if I take the 4 solutions and multiply them together, it's not so obvious from the picture what's going to happen, is it?
Is that 4 pi?
No, 2 pi.
2 pi. Okay.
Now, that's
You can
definitely
square.
a clue you can't ignore, right? That's a, wait. You take all these partition solutions and multiply them together, the product is a circle, their sum is a 0, which means a balance. So far we've constructively made a balance, a circle, and what if we, since we know we care about the squares, what if we say all of them though? And you know the answer, of course, but it's mind-blowing. Negative
Negative
4 pi. There's more. Which one do I want to do? Well, there's a bunch more. Okay, I don't need to go into the rest, and there's a whole bunch of them that you can kind of explore. These are the ones I find most centrally first impressive. There's lots of other constructive things you notice, like the value here happens to be the exact average of those two, so there's a balance there, and so on. But there's more symmetries in here you can write down, and they're fun. But we can also write them down in terms of this. So, J1, J2, Jr squared equals 2 pi also. Right, very simple ways to include writing it in there. So these 6 numbers, 4 numbers or alternate representations of those 2 numbers, are fundamental partition parameters for this division balance, right? And if we're saying the external projection of our balance is divided up by that constructive arrangement, then this is what we end up getting from all those partitions. We have a system under so many zeros, so many things that's being divided and rotated, making the balance. Now, when I do this all this hand-wavy stuff and we have zeros, I'm trying to imagine some sort of fluid that can rotate against fixed points. Those points stay zeros, they don't move, but then all the fluid around it does, okay? This was the starting point of how we just divide up the world, which means we already know the plate mass boundary is important there, but we know from our picture that there's one other boundary as we go in from the plate mass boundary, that's the charge boundary. So this should constructively tell how, as we go from the mass boundary to the charge boundary, how things get divided up. Okay, so now let's switch to talking about the charge boundary, and then we're going to talk about the mass boundary, and see how the values of the charges we need in fundamental physics and then the values of the particles of mass pop out of this automatically. First, there's one charge boundary. We call it the blank charge boundary. That's the source of the dimension of charge in reality. The only source in this plane, right? In this geometry. And that charge boundary is being acted on by this guy somehow. First way you might guess is, well, let's pick the first solution. What do you get when you multiply the first solution of our partitioning by the charge boundary? You get the one and only electron. You get the charge of the electron, which is the fundamental expression of charge we see in nature. It's also the charge of the proton magnitude, right? And so on. It's the fundamental expression of charge, the only one. Now, internally, we have particles that have partial charges of this, but they're never free on their own to do anything. The charge always comes together, right? And this is the only value, unit value of charge we care about, really, in nature. Well, we care about that one, and this is the one we always see. So that boundary is wrapped or divided by this into that. Okay, great. Kind of done with charge, but let's do a little more. Remember the splitting of 1/3 and 2/3 in the dilogarithm split at the bottom? The partition balance of all the particles, I just like to refer to pictures so I can't screw them up. Okay, we have different particles. The Z boson, the Higgs, the W boson, and they have charges. We have a proton, we have a neutron, and we have an electron. And then we also have, I'm putting these in a special order, we have 3 different neutrinos, and we have a down, an electron up, S, muon, charm, bottom, tau, and top. Right, those are all the particles in nature. Except I've repeated the electron twice. Okay, so I've got a grouping of particles, a group of particles, the electron shows up twice in those groupings. The charges that we have measured for all these, of course, everyone knows the proton, +1. 0 for the neutron, -1 for the electron. This is our base here, but the neutrinos all have 0. So our different expressions of charge that we've measured in reality have come up with these expressions. They're all in terms of the electric charge or the electron. This one's +or -1, 0, +or not +1 -1, I should say plus and -1, plus and -1, +1, -1, and the rest are zeros. But down here, the story is completely different. So this is an external expression, and every external expression is either +1 or -1 of the electron charge. So really I should say everyone is the charge boundary times whether there's a 1. They all go up here. But inside, we don't have 1s except for right down the middle. We have instead -1/3 electron charges and positive 2/3. It goes the other way. Charge is being split up in negative 1/3 and positive 2/3 divisions in every single case. Okay, which is just like the internal, by internal here I mean imaginary, internal direction or construction of our setup, of our hyperbolic figure 8 knot. So the hyperbolic figure 8 knot internally divides this way, and that's why charge internally divides this way. It's the same boundaries we're talking about.
Right.
Externally, it's arranged this way. Great, what about masses? How are we going to get to any mass construction here? Well, the mass boundary is the last boundary externally, last partition boundary going outwards, okay? So we call it the most trivial. It's where the action is kind of mostly well, it's where the action dies for partitioning. So if we wanted to think of this action, this hyperbolic figure 8 knot on the inside, since its external projection is made from the same circles and it's double cover on the inside, the waveform on the outside goes out once, and goes out twice for each hyperbolic figure 8 knot, which is a double cover. So there's four waves, symmetric 4 waves coming out, and looks very much like a helium atom. Right? But those 4 waves mean we have 2 volumes of the hyperbolic figure 8 knot that we're tracing out. But to do it, we need to use a mass boundary 4 times. We take 4 mass boundaries to trace out 2 volumes of hyperbolic figure 8 knot externally, and now we've countered the double cover hyperbolic figure 8 knot on the inside completely. Out there we've closed. There's no more partition action available anymore now, right? Because we've perfectly symmetrically closed what was available.
Yeah.
Great. Well, from there, I was able to notice that this is very, very, very close already to the mass of the electron. And here we get the hyperbolic sign of the hyperbolic sign. So this trivial inverse hyperbolic closure, we've opened the hyperbolic actions, and here now we've closed them all off, and we've closed literally all the arrangements here end. Okay, divided by the Berkeley seal symmetry, but they were also enhanced by it before, so it's done now. Great. Well, it just turns out that is literally to every significant digit, and this one we know really, really well. So when you say that, you're like, wow, that's something we can stand on now. We have a basic closing geometry that's symmetrically against the internal geometry, defining now a minimal arrangement geometrically for the mass boundaries. But there's 4 expressions of the mass boundary, right? That's the thing to keep in mind. 4 copies of itself there. Cool. But they're arranged this way specifically geometrically. Awesome. Internally this way. We know very much about it, but now its value is exactly right. Great. Well, if this is what's going on, you can imagine that boundary is then, well, like the hyperbolic figure 8 knot, which has a throat, it's splitting in 2 ways. And so if you look at it the right way, there's a plane in which it splits this way and that way. Okay? That's just required. So there's going to be another condition for this balance that determines how it splits, which will be squared. So some squared splitting condition related to this that gives us another expression. And then there's going to be, because both splits happen, but they're closing, so there's another plane in which those things are coming together. So those are the 3 maximally different ways of expressing this boundary in terms of its balance, and now in terms of the way it splits squarely, and in terms of the way it returns or closes. So far, how are we tracking so far?
Yeah, it's good.
That's really beautiful, isn't it?
Yeah, it is. Awesome.
Yeah. Now, let's go to the splitting one. We have our big twist, and that was unexpected to me. This is the part that made sense to me, but okay, cool. It's also twisting in 2 ways, great, and it's squared. Alpha Feigenbaum minus 1 squared. Let's stop there. Have you seen alpha Feigenbaum minus our equation, our constant before? Oh, great. You have some fantastic YouTube videos to watch on this. Recently, like in the last couple of years, they've been put up some great ones. It's a number that's fundamentally laced into the Mandelbrot set, or any bifurcating sequence. Yeah, it's the universal bifurcation parameter, and it has another one that comes along with it called the delta Feigenbaum constant. There's another, it's 2-dimensional relationship, so there's 2 unique numbers that really matter there, and they're in every system that does this, every bifurcating system. Okay, so it's really awesome, but there's a mystery there. Anyway, if I want something that's splitting, that would be the best splitting number to pick. Hyperbolic, I put a -1. So it's a split that's hyperbolically balanced. And I'm squaring it because I needed it to happen in this way and in this way. Now, terminally, this one is 1 minus 1/3 e to the 3 Euler-Mascheroni constant. Uh-oh, that one all of a sudden feels very, very, very fundamentally in physics. E to the 3 gamma shows up all the time. Okay, and the only other piece here was the other twist. Wait a second, we have the big twist and the little twist. Okay, what's it going to be when it comes together? Because so far, those seem like all independent pieces, but when it comes together, we have a big twist. And here, all right, and what do they equal? This one's the mass of the electron compared to proton, and this one's the mass of the neutron. So now this one gives us the neutron value, proton over mass of electron. All right, go. How would you parse that? What do you see?
Well, I see the big twist, little twist in both of them.
Good.
Except for this one's squared.
Uh-huh.
I see the
E to the 3 gamma.
symmetry here.
Okay,
in
okay, yes.
The,
Yeah, they come together,
Yeah.
right? Yeah, okay, good. And how about maybe I would guess that this is the most confusing? How would you read that? Or do you know what this number is?
no, I don't.
It's the dilogarithmic, the non-trivial zero of the logarithmic interval. The logarithmic, sorry. Yeah, so if we have the logarithmic interval, it goes like this. It has a trivial zero and it has one non-trivial zero. That's that guy right here.
Okay.
So in the logarithmic connection itself, there's 2 zeros we care about. You could actually write this whole thing as 0 plus, so both of them are in there, if you want. That's fine.
Okay.
All right, so that means there's a dilogarithmic connection. There's, what the hell does the 3 mean? And a pi. I think you know what pi means.
Yes.
Circle, what 3 mean though? The connection between what?
It's just the divisions of the 2/3, 1/3. There's 3.
As x approaches 1, and this is a hyperbola with domain from 0 to 1. As x approaches 1, this base hyperbola, not the modified one, the regular base hyperbola just goes to 1 over x is 1 plus 1 plus 1 cubed. So 3.
Oh, yeah, right, 3.
So this is saying we have a regular hyperbola
Right.
and a circle being joined under the logarithmic connection. This whole system is the projected system. Its divisions define the geometries of everything. You follow me? There's an inherent hyperbolic balance, there's an inherent lemniscate balance, inherent circular balances in the whole system, right? And they're being connected. So we're taking geometric expressions of twists and all geometric parameters and finding that geometric arrangement gives us what we needed from this one mass boundary. Yeah. Okay. Cool, isn't it? Yeah. Really cool. This is it. That's the trivial ways of expressing the balance of the mass boundary, which, because we know it's the most external partition boundary of all the actions from the hyperbolic figure 8 knot. Okay, so everything closed, we can figure all these actions out, but now we're really done. We only have 3 expressions, the electron, the proton, and the neutron, to express all that. The rest of them, they only come from us extending this pattern, from taking the same exact pattern, taking the way we split and the way we join, and then just doing it again, and doing it again.
So the fundamental mass of say the proton and the neutron would just be to solve these equations for that.
Yeah, the electron literally tells us how this balance line we're calling the mass boundary is shaped, right? We have the mass boundary of a certain size, but it's under a certain shape also. This is the balance of it. That's where, if you were to follow that action, if you trace out the whole balance line, that whole trace out is staying. It's the perpetual part. But it's perpendicularly composed. It's falling apart and coming together. So literally these are just the connections to the balance. The balance is divided by what? How does the balance divide? We know it's the balance there. Let's find the one that divides it. Okay, well that one's the other expression of it. Let's call it the proton. Or more specific, let's call it the mass of the proton. It's another expression of the mass boundary. It's the expression we call the proton mass. So the one mass boundary has intrinsically the electron's mass expression as its balance, but 90 degrees, the proton mass, as the way it divides. And the neutron reconnects those three pieces. So to reconnect them, we get the mass, the other expression. It's perfect. It's gorgeous, really.
Yeah.
Shit, I think I typoed something. Yes, I did typo something. ME over J2 over J1. I think squared to make sure. There. Yeah, that was really important. So when I did this, I didn't have this. Okay? And it's not right. It doesn't give me the number I want. What do I need? And it turns out I knew this one. So I ended up getting down to, I could find, I put that one, gets me closer, but still off by that amount. And I almost just skipped it. I'm like, okay, I don't know what's going on. I did something wrong and went on for the day, right? Instead, I thought, wait, I really recognize the number that it spits out that would be required to make this work, right? I really recognize that number. And then eventually it occurred to me, wait a second, I think it's from this, and retype the equation in and boom, yep, the second solution popped out. E is one of the most beautiful geometric numbers there are. What do I mean by that? It's defined as the infinite sum of inverse factorizations, right? N to the k. K equals 0 to infinity. Sorry.
Yeah.
There we go. So it's equal to 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial. Why do we care about these factorials? What would that matter to us?
What's 0 factorial defined?
It's 1. So yeah.
Okay.
0, nothing factored leaves you at 1. When you don't do your factoring, you're still at the system of 1. So you did 0 factoring. Yeah, and also 1 factorial is 1. This infinite inverse factorial sequence, right? Infinite in the set that it's a sum, we're adding an infinite number of them together, but each time it's a sequence that increases in what they're factoring. And it's almost like it's a thing that bumps into another thing, and so now 2 things are involved. Now those 2 things want to do something else, but the next thing they do is bump into somebody else, and now 3 things are involved. And since the things that we're talking about were elementary factorized balances, then it just goes out and out. And it's like this is almost a wave sequence of how things spread naturally, right? Okay. Well, a really interesting thing happens in terms of symmetry. If we keep this sequence the same in all of its entries, but we change the signs of every other one, right? So I'm keeping it's almost the same, but I'm making the sequence change, so the signs change. If this represents the infinite series of all factorizations, inverse factorizations, changing the order of the signs alone. So when you're putting the factorizations together, now it's instead of add another factorization, another one on them, it's almost like you reflected. Some of them you get back and forth in your factorizations. It turns out that gives you 1 over e. You get the multiplicative inverse. That's a mind-blowing, beautiful thing. Okay? So this number is central to factorized balances. It's the number that you couldn't pick another number that you could say is more central to them, right? But it's also the hyperbolic number. So remember how we said this whole thing is the trivial hyperbolic factorization? Okay. What do I mean to call this the hyperbolic number? How can a number represent all of hyperbolic everything? Well, if we generalize this equation, so now we go e to the x, same equation, then we just have to modify x to the 0 over 0 factorial plus x to the 1 over 1 factorial, sorry, plus x squared over 2 factorial and so on, right? If I break these up into even and odd parts, easier to color them that way, but it's pretty easy to tell which ones are even and odd, every other one. And then make two new series out of them. I make the even series, I make the odd series. Okay? Pretty easy. Do you know what I mean by that so far?
Yeah.
Okay. So the even one is going to be x to the 0 over 0 factorial plus x squared over 2 factorial, blah, blah, blah. And odd is x to 1 over 1 factorial plus x cubed over 3 factorial and so on. This defines the hyperbolic cosine, and this defines the hyperbolic sine. The functions. That sequence of inverse factorizations is what we're talking about when we talk about the cosine. Or this sequence, when you put them both together, when you put both hyperbolic parts together, you get the whole sequence.
Okay.
Right?
Yeah.
That's what we mean by it's the hyperbolic number. It's really beautiful, actually. In our rotations, we have a rotation 0, rotation 1, rotation 2, rotation 3, rotation 4, right? This is for time, space, charge, mass, and temperature. But there's a partition number of 44 that goes with this one, but it's this. This is b times n. This one's 18, this one's 8, this one's 32. Okay, we've gone through that a bit, but these are the partitions and rotations. All right, and I haven't written the numbers, I'm just using the symbols, but you know that we have exact numbers for all of these, not to our 14 and more significant digits, right? If we take that whole set and we add up, so we add, so this means all of our partitions, and we divide that by the multiplication of the product of all of our rotations. Here, means we add all of those, and here we multiply all of those. This is a great, simple, symmetric way to talk about your whole system. All of its partitions divided by all of its rotations. What do you get? I love it. Its main projection is the hyperbolic balance. That's it. Terminally, 1 plus the gamma function on the terminal boundary. Now, a lot of clarity comes in from this equation. A lot of clarity. We know our basic structure of our whole geometry was this setup with this piece and this piece on the terminal boundary. But here we're saying that if we put all the actions together, it gives us a system under the trivial hyperbolic balance, and that system is terminally under the factorization of the gamma function.
So you got a variable on the right hand side. The x.
Yes, I haven't explained that. Good. That's unknown so far, but this is the structure I want you to see so far. So
Okay.
in pieces, the first thing is it's under hyperbolic balance. Terminally, that thing is on the terminal boundary, partitioning into the gamma function. What's the argument? Great that you saw that. Did you really pay attention? Make it a little bit bigger. The argument in here is all of our derangements divided by Brayton scale symmetry. Like we had this before, you've seen that, but there's one more feature in here, the SLC. This is the mean line in hypercube line picking. So this is a geometric concept that says you have a system that's folded in half. So we have an external system that's a split cover, an internal system that's a double cover. So this gamma function is dividing the full set of derangements on its terminal boundary, divided by the Brayton scale symmetry and the fact that externally it's split in half. Right? That's it. All right, well, thanks.
Yeah.
And man, we covered a lot.
Oh yeah.
Man, we covered a lot. Now, first of
It's
all,
like you're
doesn't
from a
it make a
fire
lot
hose.
more sense, or doesn't it seem a lot more believable now?
Yeah.
That when we say this meshes to that balance, and you know what that means, that really we're talking about the trivial hyperbolic balance, or partition system. It's
Right.
the trivial most one you can ever make. That's all we're defining.
Yeah.
Yeah. Beautiful. Yeah, as we internalize it more and more, because I'm still doing exactly the same thing, I think what's going to come together is it'll also include a perfect explanation for primes, for all these other mysteries, as our story gets tighter and tighter and tighter. Right? We know we're on the right path, but it turns out there's cleaner ways to say things as you figure out the best way to conceive them. So yeah.
Right.